Hi and welcome to another episode from Spiral Physics Education. In this episode we're going to be focusing on Newton's second law, but we're going to be looking at resultant forces first. Then we're going to be looking at the definition of Newton's second law, and then we're going to be looking at the mathematical equation linked to that law and using a few examples of F equals ma. But to make sure that you get the most out of this lesson, it's really important that you know what scalars and vectors are, especially with some examples of those, and also how to add vectors in 1 and 2 dimensions, but especially in 1 dimension. And then you also need to know that a force is a vector, and also how to calculate weight using W equals mg. And that G is 10 newtons per kilogram on Earth. And if you're not sure about any of those, then do check out other videos on the channel to help you get up to speed on them. So let's have a look at what resultant forces are. And really, resultant forces are important, or they can be calculated easily anyway, when there are multiple forces acting on an object. And all we do is we add up all of those forces acting on an object, and we just replace it with one force. And it's much easier then to deal with one force acting on an object, and we call that the resultant force. So to put it into a clear definition, the resultant force is the overall or net force acting on a system or on an object. So let's have a look at calculating some resultant forces just to get you warmed up. So here we've got a force of 10,000 newtons acting to the right, and here we've got a force of 15,000 newtons acting to the left. What's the resultant force acting on the object? Well, the resultant force is clearly going to be acting to the left, and it's the difference between the two, and it's 5,000 newtons, so it's 5,000 newtons to the left. Okay, let's try another one. Here we've got a force of 15,000 newtons to the right. That K means kilothousand. And much smaller 3,000 newtons force to the left. The resultant force is going to be clearly to the right, and the difference between the two is going to be 12,000 newtons to the right. So that's the sort of little skill that you need to be able to do to make the most, or get as many marks in exam questions when you're dealing with much harder Newton's second law questions. So let's go on to defining then what Newton's second law of motion actually is. And there are two definitions, and one's going to be quite basic, and another one is going to be a little bit more advanced, and it depends on where you are in your education to which one you're going to be more comfortable with. If you're just at the beginning, you know, maybe year 8, year 9, or even early year 10, then the basic definition will be absolutely fine. However, by the time you do your GCSE or IGCSE exams, it's really important that you understand the more advanced definition, and you'll only know about that once you've done momentum. So it really depends on whether you've covered momentum, whether you'll get the most out of the more advanced. So let's have a look at the basic definition. And the basic definition is that the resultant force is directly proportional to acceleration, and that the resultant force and acceleration move or act in the same direction. And that's really a straightforward, simple understanding. It's quite acceptable to think of that as Newton's second law of motion in year 9 and 10. The more advanced definition, you can see from the wording in it that it is more advanced, is that the resultant force is directly proportional to the rate of change of momentum, and they act in the same direction as each other. So, like I said, if you're not sure about momentum and you haven't covered it yet, don't worry about that more advanced definition. Just stick with the basic one for the moment. So we're going to look at the mathematical result of those two definitions to see where they lead to. So the mathematical statement from the basic definition is that the resultant force is directly proportional to acceleration. So, or we can just simplify that to resultant force is mass times acceleration. And mass must be in kilograms and acceleration in meters per second, and the resultant force is measured in newtons. And we can remove all those, put some symbols in there because it's a little bit easier, to F equals ma. So this is the equation for Newton's second law. Resultant force equals mass times acceleration. Let's have a look at the result of the more complicated definition though, and see where we get to with that. So from the resultant force is proportional to the rate of change in momentum, it means that we're going to get something that has momentum over time in it. So the resultant force is equal to the change in momentum over time. And once again, if you're not sure about momentum, you don't need to worry about this section, but if you have done momentum, this should mean something to you. So change in momentum will just be final momentum minus initial momentum, and momentum is calculated using mass times velocity. So there we've got mass times final momentum minus mass times mass times final velocity minus mass times initial velocity over time, or mv minus mu over t. And we can simplify that. We can stick a bracket around the v minus u and pull the m out. So that's our equation from the more advanced definition of Newton's second law. However, what I'm thinking here is, I think I need to do that. What I'm thinking here is actually acceleration is v minus u over t. So what I can also do here is say that F equals ma, and that's very useful then. So we get to the same result each time. So Newton's second law of motion. So to summarise, we have F equals ma. But what you have to remember is that F, it's really important this because a lot of students forget, that F is actually the resultant force. It's not force, it's the resultant force. So if you're not sure about resultant force, do check out the videos on my channel to get yourself very, very clear about the understanding of what that means. That m is mass in kilograms, and that a is acceleration in meters per second squared, and we can calculate it using v minus u over t. So that's the background of the basic and the more advanced definitions, but they get to the same result. We get to this equation that F equals ma. So let's have a look at some examples using F equals ma. They're going to get progressively more difficult. So first example then. So a student is going to lift a 12 kilogram bag off the ground by exerting a resultant force on it. And it's going to be 24 newtons. So the first thing is that we've got mass and we've got resultant force. So what we can do is we can work out the upward acceleration with that. We're going to do it to two significant figures. Now because we've got mass and resultant force in the question, we can just plug it straight into this equation. We need to rearrange it first, and it's really important that you're comfortable with rearranging equations. And now we can just plug in. So we've got 24 over 12. Quite simply that's going to be 2. But it's 2.0 to two significant figures, and then we've got to remember to put the units to get the most out of our marks in that exam. So that will be a simple example or question in an exam based on Newton's second law. A little bit more complicated then. So this time the student lifts the same bag, 12 kilogram bag off the ground, but this time they're going to exert 144 newtons on it. And we're going to calculate the acceleration to two significant figures again. So the difference here is we're not told the resultant force. So we have to calculate the resultant force. We can't plug in 144 newtons as F, because that force is not the resultant force. So let's think about this in terms of diagrams. The students don't draw enough diagrams in exams, so I would encourage you to draw force diagrams and doodle on the page before you actually put your answer in or do a calculation. So first of all, 12 kilogram bag. Well, we don't know the weight of it, so we know that it's pulling it down. And we've also got force of 144 newtons pulling it up. So that's our free body force diagram of the forces acting on the bag. But we don't know the weight, but we can calculate it using this equation. Now the mass is 12 kilograms and gravity on Earth is 10. So the weight of the bag is 120 newtons. So now we can redraw our free body force diagram. So we've got 120 newtons pulling it down and 144 newtons pulling it up. So we can now calculate the resultant force. It's just the difference between the two because they're acting in different directions or opposite directions. And we get a resultant force of 24 newtons. Now we have a resultant force and we have mass. Now we can calculate acceleration. So upwards. So we've got our resultant force of 24 newtons up. We can use this equation, but we do need to rearrange it. Now we can substitute in 24 newtons of resultant force divided by 12 kilograms of mass. It's going to give us 2 meters per second squared to 2 significant figures. So that was a little bit harder because we had to add in a few more steps. So let's have a look at another example, and more complicated again. This time we're going to be dealing with a 200,000 kilogram rocket. It's going to take off from Earth, and it's going to take off at 14 meters per second squared, and it's going to go upwards. And we're going to calculate the thrust of the engines produced as it takes off. So draw diagrams again. So we've got our rocket. We've got a force acting down, which is going to be the weight of the rocket. We can calculate that. So we've got weight is mass times gravity. That's 200,000 times 10, 2 million newtons. So we've got a force of 200 million newtons pushing down. It's accelerating upwards, and that's called, so it's accelerating upwards, so there must be a resultant force acting upwards. So the thrust acting up must be bigger than the weight acting down. But we don't know the value of that thrust. So there's not a great deal else that we can do there, but we've got resultant force that we can calculate using this equation because we've got the mass and the acceleration now. So if we've got the F equals ma, we can just put the mass of 200,000 times 14 and we get 2,800,000 newtons as our resultant force. So the resultant force acting on the rocket is 2,800,000 newtons. And what we can do with that is we can say, well, if that's the resultant force, then thrust minus weight must equal the resultant force, must equal this 2.8 million newtons. Rearranging this, though, the thrust is going to be the resultant force plus the weight, and it's going to be 2,800,000 plus the 2 million for the weight of the rocket. And if we add those together, we get a thrust of 4.8 million newtons, and obviously that's going to be upwards. So that's quite a tricky question to end on. It's got lots of different calculations to do. But my advice to you would be to remember that the F in F equals ma is resultant force, and also to do little diagrams before you answer questions. Draw out a free body force diagram so you can label arrows like I've done in these questions to help you make sure that you are calculating the resultant force in the correct way before you just substitute numbers into F equals ma. So I hope that you found that episode on Newton's second law useful. Do subscribe to the channel, and hopefully that will improve your understanding of physics and help you improve your grades in time for your exams.